Imagine you're in a park, looking at a leaf on the branch of a tree. We know light bounces off the leaf to your eye to tell you it's green, but what is light, exactly? Two early ideas come from the 17th century. English scientist Isaac Newton thought light was made of little particles, he called them corpuscles, emitted by hot objects, such as the sun or fire, while his contemporary, the Dutch physicist Christiaan Huygens, thought light was a kind of wave vibrating up and down as it moved forward. Still, neither of them had a concept of what light really was. Newton had no idea what his corpuscles were made of, Huygens had no concept of what was waving. Incidentally, the question of whether a photon is a particle or wave has never been fully resolved. We can trace the first steps towards understanding light's makeup to a benchtop in Copenhagen in 1820, where Danish scientist Hans Christian Ørsted was giving a lecture on electricity. A compass happened to be sitting near the battery he was using in his demonstration, and he noticed the compass needle suddenly jerking when he switched the battery on or off. This meant electricity and magnetism were related, or, as it was more formally described later, a changing electric field creates a magnetic field. Then 11 years later, English scientist Michael Faraday discovered the opposite rang true, that a changing magnetic field also creates an electric field. It was the Scottish physicist James Clerk Maxwell who collected these ideas about electricity and magnetism, plus a few others, and pulled them together into one coherent theory of electromagnetism. But Maxwell's most celebrated insight was when he combined the work of Ørsted and Faraday to explain the essence of light. He realized that a changing electric field could create a changing magnetic field, which would then create another electric field, and so on. The result would be a self-sustaining electromagnetic field, endlessly repeating, traveling incredibly fast. How fast? Maxwell was able to calculate this too, at about 300 million meters each second, pretty close to what had recently been measured for the speed of light. And so this is what light is, an electric field tied up with a magnetic field, flying through space. You can think of the two fields as dance partners, wrapped up in an eternal embrace. To keep self-generating, both electric and magnetic components need to stay in step. It takes two to tango. Now we know that there is a whole spectrum of electromagnetic waves, each distinguished by their wavelength. You can think of the wavelength as the length of the dance step. At the short end, high-energy gamma rays can have a wavelength much smaller than a hydrogen atom, while at the long end, low-energy radio waves can be as long as the planet Jupiter is wide. Visible light is a very thin slice of the electromagnetic spectrum, from wavelengths of about 400 to 700 billionths of a meter, about the width of an E. coli bacterium, or about 1% the width of a human hair. You might wonder why we can see this range of light and not other wavelengths. There are two main reasons for this. First, vision usually involves some kind of chemical reaction triggered by light. The carbon-based chemistry of our cells happens to be kicked off by light of around the visible range. Longer wavelengths don't carry enough pep to set off the reactions, while light of shorter wavelengths carries too much energy, and can damage the delicate chemistry of life, which is why ultraviolet light causes sunburn, for instance. Second, the 400 to 700 nanometer range can travel quite far in water before it gets absorbed, which is why a cup of water looks transparent to us. Almost all visible light passes through. The first eyes evolved under the sea, and so this range of light held the most evolutionary advantage, compared with other wavelengths. And so, back to the park. When you look at the leaf, the light entering your eye is a wave of electricity and magnetism of a particular wavelength. The light hits your retina and sets off a particular pattern of chemical changes in your cone cells, which your brain recognizes as green. So the next time you see someone with nice eyes, you can compliment them on their beautiful electromagnetic wave detectors.